Show the functions are inverses of each other and discuss their domain and range. All right, so we're going to use the formal method of showing they're inverses of each other, and that method involves basically performing the composition in both directions. So we'll do f of g of x and then g of f of x. All right, so let's go ahead and do that first. So if I do f of g of x, right, then that means start with the f function and leave a space where all the x's were. So we'll have minus 4 squared plus 1. And then plug in the g function. The g function in this case would be 4 plus square root of x minus 1, right? Now, if we do that and we simplify, we see that the negative 4 and the positive 4 cancel out, leaving you essentially the square root of x minus 1, quantity squared, plus 1. Of course, if you square a square root, you know you lose the radical. So we're going to end up having just x minus 1 plus 1. And of course, we get x in that case. That's the first prerequisite. That's the first requirement met. F of g of x must be equal to x if the two functions are inverses. But it must also be true that g of f of x has to also be equal to x. So let's start with g and leave a space where the x is, right? So 4 plus the square root of space minus 1, right? In the space, we're going to put the f function. That f function will be x minus 4 squared plus 1. Then, of course, the plus 1 minus 1 will cancel out, leaving you just 4 plus the square root of x minus 4 squared. We know that the square and the square root will eliminate each other, giving you 4 plus x minus 4. And then, of course, the 4's will cancel out, leaving you again with just x. So we've shown that these two functions are indeed inverses of one another. That's the formal way to do it. Now, they ask us to discuss the domain and the range. So I want to remind you of this property here, which is mentioned in the green box above. And that is that essentially the domain and the range switch for inverse functions. So what we're going to say here is that the domain for f, so let's talk about f itself. The domain for f is as follows. It says that we are only supposed to use x values that are greater than or equal to 4, right? And so that means the domain will range from 4 to positive infinity, because those are the numbers that are greater than or equal to 4. Now, what's the corresponding range? Well, to see the range, you might think of it a couple of ways. You could think about if I put the smallest x value into that I can put in there, according to this domain, we can only put 4 in there, then I'd have basically what? 4 minus 4 squared plus 1. Well, that's 0. Plus 1 means 1. So it looks like the minimum y value we'll have is 1. And then we'll go from 1 up to where? Well, up to infinity, because if we keep putting large x values in there, we'll keep getting something that's very large after we square it, and then we'll add 1 to it. It'll just keep getting bigger. So in other words, there's no restriction on that. You could also see that from the graph, right? X minus 4 squared plus 1 is a parabola. And the parabola basically has got a vertex at 4 units to the right, because that minus 4 in the parenthesis moves it 4 units to the right, and the plus 1 moves it up 1. So we're basically from here, and this graph opens up. Now, a normal parabola would open up on both sides, right? But this one is restricted because we're not allowed to use the x values over here. So that means this left half of the curve doesn't exist. So it's just this. That way it passes the horizontal line test, and we can show that it's a one-to-one function. All right, either way, that's the domain and range, and you can see that from the graph. Now remember, for g, that must mean that what? We don't even have to think about it. If we know that g is the inverse of f, then the domain and range are just switched. So I can just say, okay, domain and range then are switched. So the domain now for the g function will be the old range, so 1 to infinity. And that means that the range for the g function will now be the old domain, which is 4 to infinity. In other words, we just switch these guys' locations. We swap them positionally, and now we have the domain for g and the range for g. And of course, if you check that, you'll see that that's in fact correct, right? Because if you look at what g is, it's basically a square root, and we know that what? You cannot put anything under the square root that will result in a negative value, right? That must mean that x minus 1 must strictly be greater than or equal to 0. And if you solve that, it means x must be greater than or equal to 1. That's exactly what we just said here for the domain, right? That it goes from 1 to infinity. And then, of course, if you look at the graph of this function, right, it's basically this graph normally. This would what it normally be, right? But they've done some transformations here, right? The minus 1 means they move it where? To the right 1 unit. So it's going to be over here instead, going like this. But then also, they didn't just do that. They also moved it up 4 units by adding 4 to it. So that means it does this, right? So it goes from here up, right? And then if you look at the range, you can see that what? The range is from 4 to infinity. Yeah, because on the y-axis, it starts here at 4 and then just keeps getting higher. So it is from 4 to infinity. So you can tell that everything fits. And again, that's another verification that these two functions are indeed inverses. Last thing I want to say about this is to talk about how you might have got the, just kind of intuited what the inverse of f would be just by thinking about what was being done to x and doing it in an exact opposite order. So this is kind of interesting, and I'm just going to mention it briefly here at the end of the video. If you have your order of operations, the please, excuse, my dear Aunt Sally stuff, right? And you think about that order, what was done to create f of x, right? To create f of x, they would have done first, before anything else, they would have subtracted 4 because that's inside the parenthesis, right? They would have subtracted the 4 first. That was our first step, right? Now for our second step, they would have what? Squared, because you'd square before you add, right? So they would have squared at that point, right? And then for our third step, they would have added the 1, right? That's how you would build that function up, following order of operations, right? Do inside the parenthesis first, then you would do the exponent, then you would add the 1, correct? Now, what about if you wanted to do the opposite in exactly the opposite order? That'd mean your third step would now become your first step, but you would want to do the opposite of add 1. You'd want to what? Subtract 1, right? And for your second step, you'd go to the squaring step, but you wouldn't want to square. You'd want to what? Square root, right? So you'd want to square root in that step. And then for the third step, where we did x minus 4, so we basically subtracted 4, we wouldn't want to subtract 4, we'd want to undo that by doing the opposite, we'd add 4. This procedure should give you the inverse that we just came up with, that's g. Let's see if that would actually work. Just a clever way to do the inverse, right? So if you have g of x, and we're going to form that by following this pattern that we just listed here, we'd take x, and we'd first subtract 1, it says, right? Then we would take the square root, it says, and then we would add 4 to that. And sure enough, that's exactly the same as g of x that we had above. So it's a really interesting way to perform the inverse. It's another way to sort of intuitively check to see if something is an inverse before you actually do it in the formal way of doing f of g of x and g of f of x. So really interesting, and I hope that's helpful. If not, of course, you can always use the traditional method. It doesn't really matter which way you do it. It always works.